All right, this is a great problem because it uses analysis. So let's see here. We want to let f from R to R be a ring homomorphism. For all natural numbers n, natural numbers do not include 0. Fn is just f1 plus all the way up to 1 n times, which is just because you do the homomorphism thing, you factor out the n and n, so it's n times f1. And f of minus n is similar. You just subtract 1 n times, so it's n of f of minus 1, which we can pull out to get f of 1, or n of f of 1. And clearly, f of 0 equals 0 because it's a homomorphism, and thus f of n equals. No, I don't want to install your whatever thing. So this holds for all n in the integers. We want to prove that this holds for all real numbers, and then we'll prove that f of 1 is 1, and then we'll be done because then it'll be the desired function. So this is for all n and z. Next, for all n over m and q, so of course n and m are integers and m is not 0 and this and that and it's reduced and whatever. F of n over m, which is f of n divided by f of m, because this is a homomorphism, or you could write this as f of n times f of m inverse. Whatever, I'm not going to deal with all that. This is defined. So f of m is not equal to 0. And so we can do the following computations. mn f1 equals nm f1, which is nm of f. Then 1 is 1 times 1. And this is a homomorphism, and so you get f1, f1. And so this equation implies, let's see here, no, don't do that. Let's see here, n times f1 we saw as f of n, so m times f of n equals, and then we do a similar thing on the other side. We combine the m f1 into f of m, and then we keep the other f1. And so what do we do now? We get f of n, we divide by f of m because f of m is non-zero, and thus we are allowed to do so. And we know by assumption m is not 0, so we can divide by both sides. And so f of n over m equals n over m f1. So fq equals q of f1 for all q in rationals. Now since q is dense in R, here's where we're going to start to do some analysis. If f is continuous, then it follows that f of x equals x times f of 1 for all x in R. So if you don't know the analytic definition of continuity, that's okay, but there might be an index in this textbook that goes over it, although that may not necessarily be true since this is an algebra textbook, and you really don't need to discuss continuity for much anything in here except for various auxiliary exercises like this. But if you're going through this textbook, then you're probably at the same stage in your math career where you'd be going over continuity as well, or at least have learned continuity in an analysis course. Yeah, because this textbook is basically at like either the baby Rudin level or beyond the baby Rudin level, one of the two. I think typically Dummen and Foote and Artin's algebra book are considered to be at the same level of baby Rudin, and this might be a little more abstract. Like maybe you'd go through this textbook if you've already gone through Dummen and Foote or through Artin. So anyway, the point is, if you can do this, you can do baby Rudin. Or Principles of Mathematical Analysis by Walter Rudin. So take that book and learn what continuity is. It's a fantastic book. So if you don't know what it is, then you've got a lot of really cool stuff ahead of you in your math career, including the definition of continuity. So learn it. So now, suppose 0 is less than or equal to x. So here we, oh, God, come on, computer. F of 0 equals 0. And if x is greater than or equal to 0, then there exists a y greater than or equal to 0 such that y squared equals x, because you just let y be the positive square root of x. So 0 is less than or equal to f of y squared, because anything squared, any real number squared will be positive. But f of y squared is, because this is a homomorphism, it's f of y squared equals f of x. So if 0 is less than or equal to x, then 0 is also less than or equal to f of x. And that's what we're going to use to prove continuity. So let's scroll down a little bit and keep that thing right there where we start with the discussing continuity. Then, or rather now, for all x and y and r, if n and n is such that x minus y is less than or equal to 1 over n, then what does that mean? 0 is less than or equal to x minus y plus 1 over n. Oh God, I'm not going to be able to fit both of these. Y minus x plus 1 over n. And why is that? Because x minus y is less than or equal to 1 over n. That's literally the exact same thing as this statement. And if you take this statement, one of these, and you basically each of these inequalities becomes one of these two equations I've written here. You can kind of look at this and kind of move the symbols around in your head and see that that should work. I'm not going to do all the work for you in that. So then this holds, and so skipping more space. So if 0 is less than or equal to this thing, then 0 is less than or equal to f of this thing. And because it's a homomorphism, we can move the f's inside. 0 is less than or equal to fy minus x plus 1 over n f1. So norm of fx minus fy is less than or equal to 1 over n f1. And so basically you can do and thus f is continuous. CTS means continuous. And so it should be kind of clear how to do a delta epsilon argument here, because given an epsilon, you want to prove a delta such that fx and y are within delta of each other, then f of x minus f of y are within epsilon of each other. So if you have like epsilon will just be your 1 over n. And so what you choose is you choose delta to be less than, let's see here, if you choose delta to be less than or equal to 1 over, delta between 0 and 1 over n times 1 over f1, then what's going to happen is if x minus y is less than or equal to delta, then f of x minus f of y in absolute values are going to be less than or equal to delta over n times f1. And so, no, just choose that. No. Wait a minute. You choose n large enough so that, I don't know, it should be kind of clear, because if you take n larger and larger and larger, basically the point is, if you take this, so this is going to be your delta and this is going to be your epsilon. And the point is, if you take delta smaller and smaller and smaller, then epsilon is going to get smaller and smaller and smaller. So the limit as basically, as delta goes to 0, epsilon also goes to 0. And that's the main point. You can make it precise, like actually take, like you'd have to do something like choose an n large enough such that, choose n such that such that for all n greater than or equal to n, 1 over n is less than or equal to epsilon over f1, then x minus y is less than or equal to 1 over n implies that f of x minus f of y is less than or equal to, in place of 1 over n f of 1, but this in turn by our choice of n is less than or equal to epsilon over f1 times f1, which is equal to epsilon. So given any epsilon, you can choose a delta, choose delta equal to 1 over, you can choose a delta equal to 1 over n small enough such that if x minus y is less than or equal to a delta, then fx minus fy is less than or equal to epsilon. Okay, so that's the actual proof if you want to go into the details. And I guess I just couldn't help myself from writing it all out and fleshing it out. I don't know. I like analysis. So this confirms that f is continuous. So for all x in R, we know that f of x equals x times f of 1. Now, f of 1 we know is 0. Wait, no. Now f of 1 equals f1 times 1 equals f1, f1. So f of 1 is either 0 or 1. If f1 equals 0, then f of r is just 0, or is just r times 0, because f of x equals x times 0 equals 0, so f of r is r times 0 equals 0, which is not equal to r. So f would not be a homomorphism from r to r. Thus, f of 1 equals 1, so f of x, and hence f of x equals x as desired, because this means precisely that f is the identity function. And there we go. We did a little bit of algebra and a little bit of kind of neat analysis, and we got a interesting result. So this completes our proof.